Everyone, I want to show you how to do a couple of kinds of modeling problems using parabolas or quadratic functions. I'm going to show you the most important kind first, then I'll show you another kind of goofy kind. I don't know if goofy is the exact right word I'm looking for, but basically I want to start with projectile motion, which is this. So the formula for projectile motion, or for the height of a thrown or shot object or whatever, is this. So this is if you're giving the distance in feet. This is if you're giving the distance in meters. They have different coefficients out here, but are otherwise pretty much the same. So we got minus 16t squared plus v0t plus h0. So t is time in seconds. v0 is the initial velocity of the object, and h0 is the initial height of the object. Now, you don't necessarily have to memorize that formula. If I ask it of you on a test, I'll give you the formula. But if you take physics, this is definitely a thing you will use. Yeah, let's see an example of how this works. So, what am I doing? Oh, that's not the right button at all. I'm looking for the next page button. There we go. So Jordan hits a baseball whose height is given by this function. H of t equals minus 16t squared plus 48t plus 3. Oh, this is in feet. You can tell because it's got a minus 16 instead of a negative 4.9. And so I want to know how high the ball gets and when it reaches that height, and then when it hits the ground, how long it takes to hit the ground. So you might say to yourself, well, how can I tell how high the ball gets based on this? Well, here's how you can tell. This is a parabola. It opens downward because it's got a minus in front of this. And so we actually know how to find the highest point of something like that. So there we go. Parabolas are going to look something like this. And your highest point's at the vertex. So to find how high it gets, we just have to find the vertex and plug in for h. That's it. So I had h of t is minus 16t squared plus 48t plus 3. So this means that Jordan hit the baseball with an upward velocity of 48 feet per second, initial upward velocity, and at an initial height of 3 feet, right? So pitcher's at his waist or whatever. So yeah, let's do that. So I know that the x, or t in this case, is minus b over 2a, which is negative 48 over 2 times negative 16, which is negative 32. So I got minus 48 over minus 32. And when you reduce that, you'll get 3 over 2. All right, I can take a negative 16 out. So I know the time that that it reaches the height, and then I just plug that in. H of 3 over 2 is minus 16 times 9 over 4, which is 3 over 2 squared, plus 48 times 3 over 2, plus 3, which is, so 16 and the 4 will cancel, and I'll have 4 left, so I'll have minus 36 here, plus 72 plus 3, which is 39 feet. So more of a clean single than a long home run. Yeah, that's pretty much it. So it reaches 39 feet high at t equals 3/2 seconds. And by it, of course, I mean the ball, but I hope that's clear from context. And then the other question I asked was, how long does it take to hit the ground, or when does it hit the ground, right? When does the ball hit the ground? Well, we can see when it hits the ground. It's right over here, right? That's on our little sketch. The thing to notice there is that's when h is 0. So h is 0 when the ball hits the ground, because the ground has no, when you're on the ground, your height above the ground is 0 feet. So I end up trying to solve 0 equals minus 16t squared plus 48t plus 3, which we know how to do that, right? We just learned how to solve quadratic equations fairly recently. So yeah, I don't see how that factors. So I think I'm going to quadratic formula that. That's going to be a bit messy, right? So I'm going to say that I'll probably end up doing the calculator. T equals minus b plus or minus the square root of b squared. So 48 squared, I have no idea what that is, minus 4 times a, which is negative 16, times c, which is 3, all over 2a, so negative 32. All right, that looks a bit messy. So I have no interest in doing that by hand. I'm just going to jam it into a calculator. I'm going to use Desmos because it'll graph it at the same time, which will be nice. Where's my Desmos? Desmos. Oh, I've got some old stuff in here. All right, let's get rid of that. So we're going to have, let's say, y, which is h of t, equals minus 16x squared plus 48x plus 3. All right, so that's not exactly the nicest looking picture. So it looks like it's going to hit the ground, I don't know, it looks like 3.061 seconds. So we're going to find that algebraically. Oh, by the way, if you want to adjust your Desmos so it looks a little nicer, I'm just going to make the y-axis go from -2 to 6, I think. -2 to 6. That seems. That's the y-axis. Pardon me. Let's try that again. The x-axis is going to go from -2 to 6. Sorry. Forgetting my variables. Maybe 5. There we go. And then the y-axis can go from -2 up to, what do we say, got up to 39 feet? So let's make it like 45. Not 645. Just regular 45. There we go. Okay. So that's what the path of the ball looks like. So Desmos will just straight up give us this answer, 3.061, but let's see how to actually do that, right? So I'm going to find out what minus b. So put this in parentheses and say minus 48 plus, now I don't need the minus because the minus is going to end up over here. Square root of b squared, 48 squared minus 4 times a, which is negative 16, times c, which is 3, all over 2a, all over, where is that? Negative 32. What the heck? Oh, sorry, my bad. I guess we do want the minus here, right? Because the negative sign in the bottom is going to change the sign of everything. So I want to make this that one. Right. So if you want to know what that is, you just you can just jam it into a calculator and get the answer. I have no expectation of you doing this by hand. This is a giant mess. This is what calculators are for. Let's use them. Yeah, so 3.061 seconds, which you can also see right here. Very convenient. Now, there are two answers to this, right? There's plus or minus, and when we do the plus, we get this one. And so that answer is not exactly nonsensical, but it's not relevant to what we're doing here because this is a t, right? This does not, the negative time doesn't make any sense, right? When was the ball on the ground before Jordan hit it? It's not a reasonable question to ask. When will it be on the ground after he hits it is much better, right? So negative time, we just throw that one out. That one doesn't make any sense, so we don't include it. But yeah, we can see everything in here, right? You can see Desmos is really good for these problems. It will find all the relevant points for you rather easily. So yeah, that's kind of all I want to say about projectile motion. We're not going to do a ton with this. I'll probably throw one of these on a test. So yeah, just remember that vertex will find the top. Vertex will find the apex. And then if you want to know how long it takes to hit the ground, that means that the height is 0 when it hits the ground. Or if you want to know how long it takes to get 20 feet high or whatever, you can do, right, you're looking for when it is at these points, right? And you do the same thing. Instead of setting y to 0, you set y to whatever you want the height to be. Or you set h to whatever you want the height to be, and then solve the resulting equation. And we know how to solve quadratic equations, so that shouldn't be too bad. So this is about 3.061, about equal to 3.061 seconds. There you go, pretty straightforward. Let me do another one. So this one's a little trickier. So this is kind of a classic problem of some farmer is making a pen for animals, and it's always pens for animals. I don't know why exactly, but it is. So Jane's making a pen for her goats this time. It's going to look like the picture below. It's got 2 separate enclosures, and it's going to be a rectangle. And she has 400 feet of fencing, and I want to know what the maximum total area she can enclose is. And you might say, well, that's not anywhere near enough information. Just 400 feet of fencing, just to cover like all this and this and this here and this and all that. We could divide that 400 up in a lot of ways. Like, how can this possibly be enough information? But it turns out it is. So let me show you how we can do that. So here's what I'm going to do, and this is a good strategy for you in general. When there's something that you need to know and you don't know what it is, call it a variable. So I'm going to make one of these sides x. It actually makes no difference which one. I'm going to do this one right here. Now, it's a rectangle, so that also means this and this are x. And her total fencing is 400. So I need it. So let's say this guy, this distance right here is y. Well, her total area, if you just look at the big rectangle, is going to be xy, right? So I have to figure out what y is. And I can't really do this with 2 variables, but I know what the perimeter is, or what the total amount of fencing that she's got. Fencing equals 400 feet, I think is what I said. So I know that, so there's a y on top here too. So 3x plus 2y has to be 400. Well, I can do a clever thing here and solve that equation for y and say that 400 minus 3x equals 2y, or divide by 2, we get 200 minus 3/2 x equals y. And then I can take this and substitute it in here. So I can say that area, let's say a of x for area, is x times 200 minus 3/2 x, which I'm going to multiply that all out. So this is minus 3/2 x squared plus 200x. You might notice that that's a parabola. And I am looking for the maximum area. Well, area is y here. So the maximum area is going to be at the vertex. And in general, when you are looking for the maximum or the minimum of something on a parabola, it's probably the vertex. Vertex is the most important point on a parabola. So we had, what was it? Let's say, I'll put it all in. A of x equals minus 3/2 x squared plus 200x. That's what it was. All right, so that's like off my charts here. So yeah, let's do this. Is that helpful? That is in no way helpful. Okay, so I need an x value that's much bigger here. So x-axis goes to, like, I don't know, 200. Is that helpful? That's the y-axis, gosh darn it. So that's going to have to be a lot bigger than 1,000. Not big enough. 2,000. All right, I think the vertex might be visible in there. X-axis is going to go over to 100. Oh my God, this is This is not big enough. Really? 3,000. Have I put in the right thing? Minus 3 halves x squared plus 200x? Is she really getting more than... Oh yeah, no, this could be, this is about 400 feet of fencing is a lot. 200 by 200 roughly would be 40,000. Okay. Okay. All right, so it looks like the vertex is going to be up in the 7,000 range. So let's make this up to like 10,000. 0, 0, 0. There we go. And this needs to go over to like 200. Okay, there we go. I fiddled around with it long enough, and now we've got a working parabola here. So yeah, so we can find what the vertex is. We'll find that algebraically in just a second. Yeah, let's do it. So there's my picture. I am going to go figure out algebraically where the vertex is. Whiteboard. So we're going to have x equals minus b over 2a. X equals minus b over 2a, which b was 200, so minus 200 over 2 times negative 3 over 2, which would be negative 3. So this is 200 over 3, which is equal to 66 and 2/3. Is my x. I think I might leave it as 200 over 3. And then the area at that x value of 200 over 3 is minus 3 halves times 200 over 3 quantity squared plus 200 times 200 over 3. So this is going to be minus 3 over 2 times 40,000. Yeah, I see why that. I see where we're going there. 40,000 over 9 plus 40,000 over 3. So this is, well, let's 3 and the 9 cancel. Leaving me a 3 there, and the 2 and the 40,000 cancel, leaving me a 20,000 there. So I have minus 20,000 over 3 plus 40,000 over 3, which is 20,000 over 3. Which is 6,666 and 2/3 feet squared. There's the area. Now, let's go see what that looks like on our picture. Right here, we're saying that we've got an x of 66 and 2/3. Is that what it was? Yeah, x is 66 and 2/3. And y is, well, we can figure that out in just a second, right? So if x is 66 and 2/3, we've got, or I want to think of it as 200 over 3 for a second. 200 over 3 here, and 200 over 3 here, and 200 over 3 here. Well, I've got 3 200 over 3s, so that's a total of 200. And that means that I have 200 feet left for the horizontal parts. Split into 2 pieces is 100 each. So there you go. So we've got y equals 100, x equals 200 over 3, which is 66 and 2/3. So there are the dimensions, and the area that we found was 6,666 and 2/3 square feet. And I think that's what I asked. So Jane should make the pen like this. area of 6,666 2/3 square feet. There you go. That's my answer. So I want to back up a second. We did a lot of fumbling around with numbers there, and I really want to concentrate more on the process that we did. So the classic, by the way, let me show you the classic standard version of this problem. Oh, pardon me. This was the thing I was doing earlier. Just get rid of that. All right. The classic standard problem is, I don't know why it's this, but it's cows against a river. So you got a river, and you're going to make a rectangular pen that looks like this. Cows. Cows go in there. All right, and so you don't have to fence the riverside. I feel like you'd want to fence the riverside anyway, because you don't want your cows wandering into the river, but whatever. And so what you do is you just call these things X, and then you figure out how much fencing you have left for that. So if you had 400 feet of fencing, you got 400 minus 2x feet left over. If you started with 30 feet of fencing, you got 30 minus 2x feet left over, right? Because there's the total minus the amount that you have to use for the sides. And then you do X times, let's add 100 feet. So X times 100 minus 2x equals the area. And then you find the vertex, and there you go. That's how it works. That is the classic. I always do it with you'll see on the homework, but I always do it with chicken coop against a barn, because I feel like that actually works. If I had a river, like literal running water with like a bank and a slope that goes down, I feel like it'd be a negligent farmer who left that side of the fence open. But that's always how it's done. That's always how the word problem is done. I'm guessing farmers don't actually do it that way. But anyway, this is the basics. In general, if there's a thing that you need to know that you don't know, call that thing X and figure out all the other things based on X. That's kind of a classic problem-solving technique. If there's a thing that you don't know, give it a name, and then you can use it, right? And then you can use that name in the problem to figure out the rest of the things in the problem. Yeah. So I tried to do a slightly more complicated one, right, with the 3 and 2 rather than 2 and 1, but whatever, it's pretty much the same thing. And then for this, you want to remember these formulas, although I will give you this formula. I will give you the relevant formula on a test problem. I do have a question on the homework that asks you to do this with letters. It's not a big deal. I don't actually think you'll have too much trouble with it. Yeah, I think that's all I want to say about modeling with quadratic functions. There aren't actually a lot of things that are quadratic functions. At least not a lot of real world phenomena that are quadratic functions. That's why you have to come up with these fencing animals on a farm problems. There's not a whole ton of other ones. So I don't want to hit those too hard, but there you go. These are your basics. All right, I think that's all I want to say. I'm going to go ahead and stop talking now, and I will see you guys in the next video.